Imagine that we go to a pond, you pick up a rock and you drop it into the water, and we say, oh, look, cool, there are ripples around the rock. And another one of you guys notes, oh, check that out, there's a leaf. And as the ripples head towards the leaf bobs up and down. If we could graph this out, we would see, and if we had some instruments rather to see this very specifically, we'd see the leaf really only goes in the vertical direction. As the wave passes along, the leaf will rise up, and it'll go back down, and it'll go up, it'll go back down. And that seems a lot like simple harmonic motion. And throughout this unit, you should see the similarities pop up all over the place. So a wave is nothing more than the motion of a disturbance. In this case, the rock was our disturbance, and the wave was carried along by a medium. All of the mechanical waves that we look at in this unit will require some sort of medium, be it water, air, or rope. And these waves carry energy and momentum. So what are the types of waves that we'll look at? They could be traveling or standing. I'll have a different video out that explores standing waves because they are slightly more complicated. So we'll hold on that and instead just focus on traveling waves with this video. It's a wave that's not confined to any given space along a motion or along a medium. So in this example, the wave can spread out. It doesn't have to stay in a confined space. I'm just thinking about the edges of a pond are kind of a confined space, but just in the immediate vicinity, it has open space, so we can consider it a traveling wave. A transverse wave is one in which the particles move in a perpendicular direction to the wave motion. The example I'll give is moving a rope in a transverse manner. So we have this rope here, and I'll just give it a simple flick up, and you can see the wave move along the rope. It's not perfect because I have it tied to the end, and the wave is actually getting reflected. So I'm only trying to give you a short view of the wave moving. And if I were to look at a particular point along this rope, let's say here's my rope segment that I'm looking at, just like the leaf, I would see that this rope segment only moves up, it only moves down, so it's perpendicular to the direction of the wave, because the wave is moving that way along the rope, but this segment is only moving up or down, so it's a transverse wave. That's different than if you, say, take a spring and stretch it out, and I'm going to just kind of flick it here, and I can feel in my hands that there's a wave moving through. You should be able to see the disturbance. I could also push it like this, and there's a wave that's occurring, and it looks something like this, where you have these compressions and rarefactions. This is our compression spot. Let me write that out. Compression and rarefaction. So the wave compresses on itself, and then it spreads out, compresses, spreads out, and that's how the wave moves about the medium. So the particles, if we were to look at one part of this, let's look at that part of the spring, it's only moving this way to the right or left at any given point, so it's a longitudinal wave. If I take a snapshot of a transverse wave, so think the rope again, at a specific point in time, my rope might look something like that. My graph got messed up. Where this is the x direction, that's the y direction, quick snapshot, nothing surprising there. But if instead I looked at one particular segment of rope over time, let's say I looked at that segment of rope and saw what it did, well, we've already said that it only will move up and down, so this should be some sinusoidal function as the wave comes in this way, that rope piece will raise up to its max point and then drop back down and raise back up and come back down, assuming that we have more wave going to the right. And this is all similar. The equations look similar. The graphs look similar. If you're dealing with a longitudinal wave, this is a position time graph in the y direction for a longitudinal wave, and it looks just the same. I'm just calling here, say, this would be my max refraction spot, and this would be my max compression spot, and the wave turns out in a similar sinusoidal function. All right, so that's our intro to waves. I'll be posting other videos to help us get the hang of this stuff. See you soon.